Alright, so section 4.2 is on subspaces. Alright, so if you know what a vector space is, then the definition of a subspace is quite easy, because a subspace is basically a vector space within a vector space. So if you take a vector space and you take a subset of that vector space, if that subset is within itself also a vector space, in other words, it satisfies my 10 axioms, then that given subset is a subspace. So we say a subset a W of a vector space V is called a subspace of V if W is itself a vector space under the two operations. And the operations in this case is whatever the addition is and scalar multiplication. Now remember that because W lies inside of V, the two operations, vector addition and scalar multiplications, those operations also apply to the subset W. So you use the same operations on the set W. Now, Theorem 1 is basically, it saves us some time. It tells us that, well, if we want to check whether something is a subspace, we don't have to check all the 10 axioms. We can check just two things. So if W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following conditions hold. Okay? So all I have to check is two things. I have to check number one, which is basically I need to take two vectors U and V, and I just need to check that addition, adding the two vectors, is going to be again inside the set W. In other words, what this means is W is closed under addition. Number two is for a scalar K and U a vector in W, I just need to check that the scalar multiple of U, U, is also in W. And if that is the case, we say that W is closed under scalar multiplication. Now, if these two properties hold, then we say that our subset W is a vector space. So why is it that we only need to check two of the axioms and not all 10 of them? Or not the remaining 8, I mean. All right, let's go, just for a moment, let's go back to our vector space axioms. Okay. Right, so basically you'll see that the first axiom, closure under addition, relates to that property there, and closure under scalar multiplication relates to this property here. Okay, now that is the two axioms that I have to check. Now the question is, why do I only have to check this axiom? Why is it only sufficient for me to check these two specific axioms? Well, I don't have to check number 2. Okay, I don't have to check number 2. Why is that? Because I don't have to check commutativity, because if V is already a vector space, it means commutativity holds over the whole of V. Now, if commutativity holds over V, then it means commutativity holds over W. All right, what about property 3? Which is the associativity property. Now, again, if associativity holds over V, V is already a vector space. So if associativity holds over V, then associativity will hold over W. So again, just check here. Here you've got V, and there you've got W. If associativity holds over the whole of V, then that's going to include W as well. So associativity is going to hold for that that space there. Okay, that subset. What about? Okay, so let's leave property 4 and property 5 for just a moment. If we look at axiom 7, Now axiom 7 will also hold, because if distributivity holds for V, then distributivity, well, if distributivity holds for V, the whole of V, okay, then distributivity is going to hold for W as well. Right, so that is that. Then property 8, if this distributivity law holds, again, if it holds for V, it holds for the whole of V. And so it's going to hold for W as well. Okay. Right. Then, if you look at property 9 and property 10, both these properties, again, if it holds for the whole of V, then it is definitely going to hold for, it's going to hold for W as well. Right. So the moral of the story is basically that I'm interested in property 1 and property 6. What I need to show to prove theorem 1 is I need to show that I've checked the axioms 2, 3, 7, 8, 9, and 10. What I need to check is I need to check these two axioms. I need to check that they hold. So does assuming 1 and 6, if 1 and 6 hold, will that then guarantee that 4 and 5 will hold? That's what I need to establish. Okay, so assuming 1 and 6, will that imply 4 and 5? In other words, will it imply that there's a zero vector in W, or will it imply that the zero vector will lie in W? And will it imply that every vector in W has a negative? All right, so we're going to prove theorem 1. Okay, so so there we've got our V and we've got our W, and what we're going to do is we're going to assume. So we're going to assume that 1 and 2 hold. Alright, so that is that we've got closure under addition and we've got closure under multiplication, on a scalar multiplication. Okay, so this whole set here is basically closed. It's closed under the two operations, which is a vector addition and scalar multiplication. So, right, so we say that, again, note that that axioms 1, well, axioms 2, 3, 7, 8, 9, 10 hold, okay, and by assumption, axioms we said 1 holds, which is closure under addition, and we said 6 holds, which is scalar multiplication. Okay, so now take that information and just place it there. And what I'm going to do now is I'm going to continue by saying what? What we're going to do is we're going to all right, so we're going to take a vector in W. All right, then we know that. All right, now since 2 holds, which is closure under scalar multiplication, we have that the negative of this vector is also in W, because remember we said that if you make your scalar -1, okay, we proved previously in section 4.1 that that is in fact the negative of the vector. Okay, that's the negative of vector is a scalar multiple of the vector u. All right, so now we're going to apply property 1. Now you can also say since 1 holds, we have that if we sum u to this negative vector, if we sum these two vectors, the end result is, we know it's the 0 vector, but we know that by 1, we know that w is closed under addition. So if you add the vector u to its negative, that is again going to be inside the set w. So therefore we can clearly see that the 0 vector is in w. Alright, so taking that information, placing it there. Thus, what can we say then? From here, from there, we have that axiom, the 0 vectors in w. And that is which axiom? It's axiom 4 holds. It holds for w. Okay, so axiom 4 holds, so all we need to do is we need to show that axiom 5 holds. Alright, so we need to show axiom 5 holds, and that's actually very easy to see because we know that 2 holds. Now recall that, if u is a vector in w, then we know that -1 u is within w as well, and that follows from property 2. W is closed under scalar multiplication. So you can then say that, well, remember that is equal to, it's equal to the negative of the vector u. Okay, so the negative of any vector is also in w because of the scalar because of property 2. All right, so thus axiom. So axiom 5 holds. Axiom 5 holds. All right, so so W is a vector. W is a subspace. It's a subspace. Okay. Alright, so it's a subspace. Okay, so all you need to do to check whether a given set is a subspace is you just need to check that property 1 and property 2 holds. Scalar multiplication holds, vector addition holds. Alright, now it's important to note that every vector space has at least 2 subspaces. And the 2 trivial subspaces, well it's called... they are called trivial. It's the space itself, right? So what they say there is W is a subspace of itself, right? Any vector space is a subspace of itself because it is closed under a vector addition and it's closed under scalar multiplication. So any vector space is a subspace of itself. So V is a subspace of V. And also the zero set, in other words, a set that contains the zero vector, that is a subspace as well. Because why? The set containing only the zero vector is closed. If you take, like if you take as an example, if you take the zero vector and you add it to the zero vector, it is going to be the zero vector, which is going to be in W. Okay, so 1 holds. W is closed under addition. And then also W is closed under scalar multiplication, because if you take any scalar, now look, if you guys go back in your notes in section 4.1, then we did a theorem which said if you take a scalar multiple of the zero vector, that is going to be the zero vector. Okay, so I mean that is also in W. So 1 and 2 holds. Therefore, W is a vector space. W is the zero vector is a subspace of any vector space. So those are the two. Properties that you need to check to verify that a given set is a subspace. Now, an important observation is if W is a subspace of a vector space, if it's a subspace of a vector space V, then W contains the zero vector. Okay. If the zero vector is not in the set, it can't be a subspace. So what this just tells us is that's sometimes a quick way of establishing whether a given set is a vector subspace or not. Like if you can quickly see that a set doesn't have the zero vector, you can immediately see it's not a subspace. So that's in some cases a good way of checking first whether something is a subspace. Just verify first if it has the zero vector or not. All right, there we've got an example. Some examples here. They ask us to prove or disprove that the following subsets are subspaces of the relevant vector space. Okay, so we are going to look at whether which of these sets are subspaces or not. All right, so there the first one they ask me is what is W? W is a subset of M22. Now, what is M22? The set of all 2 by 2 matrices, and it consists only of the diagonal matrices. Okay, so the diagonal matrices are these matrices where you've got 0 everywhere except on the diagonals. Well, you could also have possible zeros on the diagonal. The point is just the diagonal matrix is a matrix where you have you've definitely got zeros everywhere other than the diagonal. Okay, so is this given set W, is it a vector space? Is it a subspace? All right, so there we've got A, and what we're going to do is we're going to check whether it's a subspace or not. So what I'm going to do is to check this, so you take 2 vectors in your set, and let's call that A0, 0B, and let's call the other one C0, 0D. Okay, now then if you add the 2 vectors, what do you get? Now M22, the default operation there is normal matrix addition. Okay, so we haven't changed the operations. If they don't specify which operations you're working with, then you can assume the default operation, which is in this case is vector addition. So that then becomes A plus C, 0, 0, D plus B. Okay, and this matrix here that I've now have, this matrix here, is it in W? what needs to happen for a matrix to be in W? It has to be diagonal matrix. So this, it's clear that this thing is in W, okay? And the reason is U plus V is a diagonal matrix, okay? So that's the rule that governs membership to W, is that for a matrix to be in W, it needs to be diagonal, be a diagonal matrix. So U plus V is a diagonal matrix. It's a diagonal matrix. Okay, so therefore it's in W. How do we check the second property? Is we need to check scalar, that scalar multiplication, the scalar multiplication property holds. All right, and that's not difficult to do. So let's place that there. All right, then so you're going to take a scalar. So let k be a real number. Then what do you get? If you multiply k with u, we use the default operation, which is a scalar matrix multiplication. So that becomes, you multiply each entry in your matrix with a scalar k, and so that becomes the scalar multiple. And is that an element of W? It is. Why? Because KU is a matrix, and it is a very specific matrix. It's a diagonal matrix. Okay, so it's a diagonal matrix. And remember what we said here, that it is in W. And the reason for that is KU is a diagonal matrix. All right, so it's a diagonal. It's a diagonal matrix, right? Okay, so what is the conclusion? The conclusion is that your given set is it's a subspace. So you can just say, yeah, I should have done that before I've drawn that block there. Hence, W is a subspace. Right, it's a subspace by our first theorem. It's a subspace. All right, the next one. So let W be a subset of F minus infinity, positive infinity. Go back to in your notes on section 4.1 and go and look at the definition of F minus infinity, positive infinity. It's basically all real valued functions from negative infinity to positive infinity. And W is defined as follows. It consists of all non-negative functions. That means that W is defined as follows. It's all functions f of x that are strictly bigger than or equal to 0. And it's for all x's. Okay, now is this a subspace or not? To establish this, I need to check two things. I need to check scalar multiplication and vector addition. So now what I'm going to do is I'm going to try and show whether this is a subspace or not. So what I'm going to do is I'm going to let let f of x equals 1. All right, for all x's, minus infinity, positive infinity, okay, for all x's. All right, then, right, we know that f of x is in W. F of x is in W because, why is f of x in W? because we know that f of x is 1, and 1 is bigger than 0. Alright, so that is clear that 1 is bigger than 0. So if f satisfies the condition that needs to hold for a function to be for a function to be in W. Now, alright, now let's take a scalar, and let's take a scalar minus 1. Then, if you take k, f of x, the scalar multiple, we know that is equal to minus 1 times the function f of x. And f of x is 1 for all x's. And what is 1 times negative 1? It's negative 1, and negative 1 is strictly less than 0. So is k f of x in W? That implies that k f of x is not in W. It's not in W. Okay, so there we go. Alright, next one. Let W be the subset of N22, and it consists of all matrices with the following property. Right, so it's a matrix with the diagonal, and then it's got the entries 1, 1 on that diagonal there. Okay. Now the question is W a subspace or not? My feeling is that it won't be. So so what I'm going to do is I'm going to just take two vectors, U and W. Let's take two vectors there. Let's call that. Alright, and let's call V be this matrix. Alright, given U and V, we can then add U and V together, and you can then basically just remember the default operation. Unless they specify an operation, you assume that it's the default operation, which in this case is normal matrix addition and matrix and scalar multiplication. Alright, so there we've got our matrix. Now the question is this matrix within W or not? Well, that is not in W. It's not in W because what needs to happen for a matrix to be in W? What needs to happen is these entries here, they need to be 1, and in this case you see here we've got 2 on that diagonal there, so that's definitely not in W. Okay, so that is definitely not in W. So what is the conclusion we can derive? Thus W is not a subspace. It's not a subspace. It's not a subspace of M22. Alright, and it's not a subspace because it's not closed under addition. It's not closed under addition. Alright, so those were a few examples of subspaces and non-subspaces. So just a few examples here of, in fact, subspaces. So C minus infinity, positive infinity, is a subspace of all real valued functions from negative infinity to positive infinity, and C consists of the continuous functions from negative infinity to positive infinity. Why? Because if you sum two continuous functions, the end result is a continuous function. And if you take a scalar multiple of a continuous function, it's also a continuous function. When is a function continuous? When its derivative exists everywhere. Okay, and we know the derivative is defined in terms of a limit from the left, limit from the right. That limit holds for all x's. Then you've got C1 minus infinity, positive infinity, and it's also a subspace of f minus infinity, positive infinity, and it consists of all functions with continuous derivatives. So if you take the sum of two continuous derivatives, it's also going to be continuous. And if you take the scalar multiple of a continuous derivative, then that's also going to be a continuous derivative. Cm is also a subspace of f minus infinity, positive infinity, and it consists of all functions with the first m derivatives being continuous. And again, the sum of the mth derivative of two functions, we know that the derivative distributes over the sum, and again, that's also going to be continuous, and the same holds for the scalar multiple. And also C infinity is also a subspace of f minus infinity, positive infinity, and it consists of all functions with derivatives of all orders on minus infinity, positive infinity. If a function has all its derivatives of all orders, then clearly it's going to mean that if you sum the two together, sum two of those functions together, that end result is also, or its nth derivative is also going to exist for all m, and the same for the scalar multiple, because the derivative distributes over the sum and the derivative distributes over scalar multiples. There we've got an example of a polynomial of nth degree. I'm just writing it out just to refresh your memories. That's an example of a polynomial. Now, P infinity is just a polynomial of infinite degree. So that is going to be a polynomial where that degree is going to go to infinity. Okay. And that is a subspace, because what happens if we add two polynomials together of infinite degree? You again get you gather your like terms, your corresponding x terms, and then you end up with again a polynomial of infinite degree. What happens if you take a scalar multiple of a polynomial of infinite degree? You get again a polynomial of infinite degree. Then Pn is the subspace of Pn is the subspace of f minus infinity, positive infinity, and it consists of all polynomials of degree less than or equal to n. Now, this polynomial here, will be an example of a polynomial in Pn because it's got degree n. So that's so again, if you sum two polynomials of degree less than or equal to n together, you're going to get a polynomial of degree less than or equal to n. And if you take a scalar multiple of a polynomial of degree less than or equal to n, then you're going to get a polynomial of degree less than or equal to n. So it's clear to see that all those sets are subspaces. Right now, you can also go and see that Pn is clearly contained in P infinity, and P infinity is contained in C infinity, because polynomial of infinite degree is infinitely differentiable, and C infinity is obviously it's contained in all the polynomial, or all the functions that have mth derivatives, and that any function that is an mth derivative also has one derivative, so it's in C1, and any function that has one derivative at least is definitely going to be a continuous function, and any continuous function is definitely going to be in F. All right, so you've got that you've got that containment chain there. All right, Theorem 2 says basically that if you have a vector space and you've got this sequence of subspaces, right, then the intersection of these subspaces is also a subspace of V. All right, so let's look at why this is in fact the case. Why is the intersection of subspaces, why is that a subspace? So what I'm going to do is I'm going to let W be the intersection between all these subspaces. And now the question is this going to be a subspace, right, of W? Okay. So what I'm gonna take W to be this the intersection, and then I'm gonna let right, let me just fix that. Let that and U and V be two vectors in W. Okay, now right then, now if U and W are both in the intersection between all those two subspaces, that implies that U is in every one of these spaces, and V is also in every single one, and that is for all I, indices I that run from 1. Okay, so the indices there run from 1 to up until R. Okay, so the indices, those are the indices, 1 up until R. And that implies that now I can take the sum of the two and see what happens, because I need to apply that theorem of mine. Now, is the sum between these two in the intersection of all those sets? So that is clearly in WI. Okay, why is that? Because we U is in WI, and V is also in WI, and we know that WI and U are well. WI is a subspace. That is true for all I running from 1 up until R. Okay, and again, just note that WI is a subspace. Remember we said this. It's a subspace of V. And it's true for all I's. Okay, we assumed it there. So we can therefore say that that implies that right. So W which is the intersection between all those sets. We can then say that because this is true, that is going to imply that that the vector U plus V is going to be, because it's in every WI, it means it's going to be in the intersection between all the W's. Sorry, that should be an intersection. Okay. WR, and we know that that is W. Okay, so W is closed under vector addition. Okay, now we need to check the other property. And that is scalar multiplication. All right, so what I'm going to do is let K be a scalar. Also, so if you take KU, KU is going to be in WI. It's going to be in WI for all I. For all I between 1 and R. And because KU is, and why is that? Again, because WI is a subspace for all I. So it's closed under scalar multiplication. So that's going to imply that KU is definitely going to be in the intersection. It's going to be in W1 and it's going to be in W2. And it's going to be in W3 up until it's going to be in WR. Okay. Remember the intersection. If W is in the intersection, if KU is in the intersection between W1 and W2, it means it's in both W1 and W2. And if it's in every WI, then it's in the intersection between all the W's. All right. So, so by our theorem, we can say that this is in fact. We can say that hence W is a subspace. It's a subspace. It's a subspace. Let me just fix that. It's a subspace of V. So the intersection between subspaces is always a subspace. Now the question becomes, is the union of subspaces a subspace? All right, let's look at the following question. Here they say, they ask me something very specific here. Like, okay, so suppose we've got W1 and we've got W2, and these are both subspaces of the vector space V. Okay. Now suppose for some given element U in W1 and for some element V in W2, U is not in W2 and V is not in W1. Is the union between these two sets a subspace of V? We know the intersection is a subspace, but is the union in this specific case a subspace of V? So let's go and investigate this. All right, so let's go and see if, in fact, the union is a subspace or not. Now, I've got a feeling that this is not the case. All right, so I'm going to claim here. I'm going to claim that. All right, I'm going to claim that W1 union W2 is not a subspace. So I'm going to assume to the contrary. I'm going to assume W1 union W2 is a subspace. Let's suppose it is a subspace. All right, then I know that my 10 axioms hold, there's closure, there's all of that. All right, so W1 union W2 is a subspace, so therefore it is closed under addition. So this implies that surely you can take the vector u plus v, and that is definitely going to be in W1 union W2. Now maybe it's just good to draw a diagram to see what are we actually working with here. Here's V, here is W1, that is, let's call that W1, and here is W2. They have an intersection because they both share at least the zero vector. That's W2. And there is U1. There's U, and there is V. So V is in W2, but it is not in W1, and U is in W1, but U is not in W2. So that's a diagram that gives us more or less an idea of what we're working with. So therefore, if U plus V is in W1 union W2, we know by union means it means U plus V is either in W1 or U plus V is in W2. Either one of those hold. Okay, now from there we can say the following. Alright, so that implies that U plus V is equal to W1 or U plus V is equal to some W2 in W2. Alright, now right, so this implies that either V is W1 minus U, okay, or U is W2 minus V. I just want to make a point that we said that, remember, U is in W1, we said this, and because W1 is a vector, is a subspace, because this is a subspace, we have that it's closed under addition and scalar multiplication. So we can say that, remember, this thing we know is in W1, and also this negative of U is also in W1 because it's a subspace, right? So therefore, what happens if you add two things in W1 together? That is going to be in that's going to be in W1. This whole thing here is going to be in W1 because W1 is in capital W1 and minus U is in W1. And if you add the two, you have again something in W1. Now this is in W2 and this is in W2, and the negative of this is also in W2. So if you add the two things together in a vector space, you have that is in W2. Okay, so what is the contradiction here? So this implies, again, this implies that V is in W1 or U is in W2. But what's the problem? The problem with this is we said initially that V is not in W1, and we also said that U is not in W2. All right. So the contradiction is, this contradicts the fact. So this contradicts the fact that we said V is not in W1, and we said that U is not in W2. Okay. So, I mean, here you have a problem here, because here you say either V is in W1, and if V is in W1, we contradict this fact, and or we said that U is in W2. But if U is in W2, we contradict this fact. Okay. So it's a contradiction. So thus, the union of W1 and W2, it's not a subspace. It's not a subspace. Okay, so is it true the intersection is always a subspace, but in some cases the union is not a subspace, particularly if you have one element in the one subspace that's not in the other one and vice versa. Then you start getting into problems. Under certain circumstances, the union can be a subspace, but there are plenty of examples where union of subspaces is not a subspace.